All right. So I don't think it's going to be quite into the deep end because people are going to be talking about the higher end kind of applications we've been using mass cytometry for over the next couple days. But I'm going to give you guys a little bit of an introduction to the technology and talk about kind of how we used it, why we needed it, and some of the basics behind it. So I say guilt-free because, and I really mean it, because the thing with this technology versus where I think Peter was trying to bring stuff up in fluorescence is a lot of the time with a lot of the fluorescence measurements, when you bring one more parameter in or you change something up, you always have to be careful of what's happening everywhere else. And there's always seems to be trade-offs. And I feel like here with the mass cytometry platform, one of the benefits, well, it might not perform as well in a head-to-head comparison in the best cases of fluorescence, that overall there's less trade-offs when you're getting more data and more information. So the caveats of single-cell analysis, I mean, Gary did a great job of kind of bringing you guys into why we like high-dimensional data. But the currency of single-cell analysis is parameters. And accessing the most interesting cell types, I think most people think, come at the cost of parameters, especially some rare cell populations, stem cell populations, because you've got to gate out all your mature cells, drill down to the rarest cell types, and then you've got to have parameters to positively identify them. And the problem is when you're doing that, that doesn't leave you a lot of parameters left to start asking questions like Gary was saying and what Peter was talking about with phosphorylation of cellular behavior. So are the cells turning on certain pathways? Are they dividing? Are they dying? What are they doing in response to your drug or your cytokine that you're giving them? And so, so that, and then also, I guess I got this out of order here, multiplexing. When you start bringing in things like barcoding that are going to be Eli's going to be talking about either later today or tomorrow, that uses more parameters. And this is, of course, a problem when you don't have a lot of sample. So if you have something like a clinical isolate or something that comes out of some small little piece of a mouse, and you can only run so many samples in the machine, you need to ask as many questions as you can with that one sample. And all of this comes back to why parameters are limited in single-cell measurements. So fluorescence is a great technique. It can be very quantitative. It's very sensitive. And I think in our lab, at least, well, I think realistically in our lab, more like 9-ish colors is routine. We would say 12 colors is routine. 18 colors has been reported, but this isn't simultaneous. Only about 10 of these were simultaneous parameters, and the rest of them were mutually exclusive. So it's really hard to get into the double digits with fluorescence. There's a small percentage of people in the world that can, I think, properly optimize these experiments, and they take time. So with mass cytometry, the idea is instead of using fluorophores as reporters, we use pure mass isotopes. And looking at this spectrum here, you can see just from this illustration that the big difference is you don't have what we call spectral overlap. So in the case of fluorophores, the emission of one overlaps into the next, and there's lots of tricks to get around that, but ultimately it's a physical limitation. Where in mass spectrometry, tell the difference between 150 and 151 is very routine. My previous work in graduate school, I was working with a postdoc who was measuring two molecules under a certain state that differed by the mass of only a few electrons. And so that's possible in like a research setting. So telling the difference between plus or minus a proton or a neutron is trivial. So in atomic mass spectrometry, there's about 100 non-biological isotope reporters available. It has a large dynamic range. In some aspects of ICP-MS, the dynamic range is almost 10 to the 9. So you can measure from 1 to 1 billion with linearity and quantitation. This technology is not quite there yet, but I'll talk about that in a little bit. The other thing to point out here, because there's a little bit of confusion between atomic mass spectrometry and protein mass spectrometry. Atomic mass spectrometry is about 10,000 times more sensitive than protein mass spec. And that's why we can do single-cell measurements in this case, where in protein mass spectrometry it's a little bit more difficult. You need a lot more material. So where do these reporters come from? You look at the periodic table, I'm telling you, okay, we're using elements as reporters. Well, you look at the periodic table, there's only about 100, just over 100 elements total. But like I said, we're not measuring elements, we're measuring the masses of elements. And so when you look at something like europium, the the atomic mass of europium is 152. Well, there is no europium-152. It's actually a 50-50 mixture of 151 and 153. And when you go back to the periodic table and you look at all the other non-biological elements, they have a number of stable isotopes. These are non-radioactive isotopes that have a variety of masses. And so most of these can be, especially down here, the lanthanide series, can be measured simultaneously and quantitated without their signals interfering from one another. Of course, this is assuming you can get them all pure. So the instrument that you guys will get to see when you come back to the lab this afternoon that we used to do this is the mass cytometer. Basically, it's an ICP-MS back here. You see the plasma on in there. And they've hooked up kind of a single-cell introduction device into the front end. The cells are sprayed in, and this is where the plasma happens, and I'll talk about that in a little bit. And the cells are sucked in, and you basically acquire an elemental mass spectra for each cell. So the workflow, and I'll just breeze through this quick because Peter did a nice job of introducing the Nolan Lab dogma of flow cytometry. So we have our cells, you treat them with different conditions, drugs, cytokines, whatever. We fix the cells biochemically so that they stop what they're doing, and we kind of have that snapshot of cellular behavior in time. Permeabilize the cells and stain them with antibodies. Instead of containing fluorophore reporters, the antibodies are labeled with metal isotope reporters. And I'm not going to go into a lot of details about how the labeling works because Matt's up after me, and he's going to give you guys everything you want to know and more about isotope antibody labeling. But take my word for it. Using a commercially available reagent, we can attach somewhere between 100 and 200 metal isotope reporters per antibody. Each antibody has a unique mass that serves as a reporter, and then the cells are stained using very similar protocols to fluorescence flow cytometry, and you guys are going to get to see this for the first time firsthand over the next 2 days, where we're going to be staining the exact same sample using fluorescently conjugated antibodies versus metal isotope conjugated antibodies. And the metal isotope conjugated ones are then sprayed into the machine through something called a nebulizer. It's kind of like the sorting tip of a FACS cell sorter, so you get single cell droplets spraying out of it. It's not nearly as well controlled, unfortunately, so we lose a little bit of material on the front end, but the droplets that get past the initial chaos of the spraying make it to the plasma. So the plasma is basically argon gas being passed through a copper coil, and the copper coil is a radio frequency coil with a very high amount of energy being put into it. So what's happening is there's a few thousand watts of energy being put into this coil, and the field's oscillating really fast. All of the argon atoms get really, really excited, and we throw a little bit of a spark in there. Those electrons hit an excited argon atom. It kicks off some more electrons, and it's this chain reaction. You end up with this cloud of positively charged argon atoms and electrons. And it's net neutral, but it's very, 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 very high energy. So it's about 7,000 degrees Kelvin, surface of the sun. So as every cell goes in there, or anything goes in there, it's completely vaporized, and most of its elemental components are ionized to the first ionization state. So everything gets an electron ripped off of it. So the cell turns into a cloud of elements, a cloud of elemental ions. Those elemental ions are sucked into the mass cytometer. The biological low mass ones are kind of filtered out, and then the heavier isotope reporters are then quantitated on a cell-by-cell basis. So what you end up with is an elemental mass spectra for each cell, and the levels of each element in that mass spectra then correlate right back to the levels of each of the antigens that they were reporting for. So it looks much like flow data, where you have your different cell populations, and you can drill down on one cell population and start looking at phosphorylation responses, for instance. A little bit more about the schematic of the machine. The original publication describing the optics of the machine is here, but it's essentially a quadrupole time of flight machine, whereas the cells go in, like I said, they're sprayed. The ions are then passed through. This is where the filtering happens, so the light ones don't get through, and then the mass measurement and quantitation is done by time of flight mass spec. So time of flight, easiest type of mass spec there is. Everything's pushed down a long tube with the same amount of energy. The lighter things get to the detector before the heavier things. And based on how long that takes for that to happen, we know the mass. And based on the number of things hitting the detector, we know how much of it there is. Other reagents we have at our disposal. So other than the mass isotope reporters, there's also a DNA intercalator. And this is important. This intercalator is a really handy reagent because the machine doesn't have any light scattering properties. And like I said, we remove all of the biological elements. So if I just take some blood from anyone in this room, unless you've been to Chernobyl lately or have had, chemotherapy or MRI contrast reagents, I would think the machine's not working because your blood won't even show up. I won't see anything. It'll actually be blank. And so what we do is, for a baseline in every experiment, we add these commercially available metal intercalators where there's a metal encoded in them that we can see. So if your cell's negative for everything we're measuring, we'll at least know that there was a cell there. So what this actually looks like when you're running the machine, and you guys again get to see this, so I'll just go through this really quickly, is this is what in our lab we call the rain. So there's not nice little dot plots that come up, unfortunately. We're still working on that, but you get this kind of qualitative readback where each column here is a different mass isotope reporter, and then each line is what they call a push number. So the mass cytometer is actually acquiring about 80,000 mass spectra per second. That's not 80,000 cells per second, that's 80,000 mass spectrum. Much like a fluorescence flow cytometer has the lasers flashing much faster than the cells are actually passing through the machine. So what happens is as each cell goes in, the cloud of ions is measured multiple times, and you kind of get these blobs that show up. And if you line the blobs up by the DNA intercalator, which is these two columns here, when one cell goes through, you can see that, oh, well, this is a CD4T cell. And then only microseconds later, you've got a CD20 positive B cell coming through. And so this is literally what you're seeing as the machine's running. This is only a very, very small percentage of what's actually being acquired, but it's kind of a visual readback for you. And the idea here is to show you that, individual cell events are being acquired, and that there has to be a little tiny bit of space in between each cell event, because if you can't see space in between each cell, neither can the software or the machine. So now that we've got kind of the basics of how it works, I'm going to show you guys a little bit of QC data for when we were putting the CyTOF through its paces initially when we first started doing some of this work. So one of the cool things about the dynamic range that I was talking about is right now the current commercial instrument's linear over about 4 orders of magnitude. So if you between 1 and 10,000 counts per cell, if you double the amount of metal you put on the cell, you get double the amount of signal, which is great. And that doesn't always in fluorescence, theoretically, like our LS R2 measures up to 10 to the 5, but it's not really linear over 10 to the 5. It does start to saturate. I mean, this will start to saturate too, but the other thing is our counting, it does actually start at 1. So when you put the blank cells through, there really is no background that comes up. So this is handy if you have things that you can measure in this range. The other cool thing, and this comes to kind of a workflow ease of use issue, is unlike in fluorescence where you have something like PE and APC that are very bright, and a lot of your other fluorophores can be sometimes half or a quarter or a third as bright as those ones. Most of the metal isotope reporters that are commercially available on the mass cytometer right now perform relatively equivalently. So the idea is that once you have something on a certain channel, there's no real reason to switch it to any other channel. One, because switching it to another channel isn't going to help you. And two, because if you have something else in your assay that has a higher signal or a lower signal, because there's no spectral overlap, you don't have compensation issues that come up. So a lot of the time, I have my panel set. I change one parameter. That parameter happens to be bright, so now it's bleeding into a whole bunch of weaker signals. And I've got to swap my whole panel around. In the case of mass cytometry, this is an advantage that it has, in that it overcomes this issue. And so across the entire mass range, from about 140 up to about 180, the difference in sensitivity is only about 2-fold when you put the same amount of material in the machine. So with all of this in mind, Peter, right before when we were kind of, all these experiments were culminating, helped, Peter really designed this experiment. I can't take any credit for it. I was like, Peter, what's the hardest but routine phosphoflow experiment we can do? And we decided it was a 9-parameter experiment, 7 surface markers plus 2 phospho markers. And what we did is actually very similar to what you guys are going to do today and tomorrow, is we stimulated the same PBMC sample, split it into 2, and then did the surface marker staining and intracellular staining for a bunch of different cytokine responses. And this is what the fluorescence flow cytometry data looked like, and this is what the mass cytometry data looked like on the exact same data set. And so I'm just going to go quickly through the gating. Again, you guys are going to get a little bit of hands-on with this, so this is just more for a quick demonstration. The big difference, again, no scatter properties. So where you'd have your normal forward side scatter gate for blood, here we use the DNA intercalator and an instrument-derived parameter called cell length. And cell length is just kind of how long the signal was in the machine, not necessarily how big the cell was. And then the other big difference is I cheated a little bit, and the mass cytometry experiment was actually 10 parameters. I threw in CD45 because CD45 actually gives you a little bit of resolution between your different blood cell populations. Your platelets and neutrophils are going to fall differently than your monocytes, and they're going to fall differently than your lymphocytes. So CD45 ends up in a lot of our blood-based experiments. But once you gated out the monocytes here, gating all the lymphocyte populations was pretty much identical. And if you believe my gates here being the same, then I'll tell you that the frequencies you get in both cases are basically identical. And you can drill down on one of the populations, in this case the naive CD4 T cells, and we can look at the phosphorylation responses to the different cytokines that we applied. And again, just a summary of how it all went down. The patterns you get are almost identical. The scales of both of these are the same. A little bit different here. So Peter was talking about fold change before. I don't have to put on the board, but here what we did instead is we did the arc sign H difference, or it's kind of like a log difference. And the reason why we did that instead of fold change is unfortunately, or fortunately, I don't know if it's good or bad, with mass cytometry data, again, with the negatives actually being 0, with your unstimulated cells having no measurable signal, fold change versus 0 can get a little crazy. So dividing like 100 counts versus 0.1 counts, you can get an unusually large fold change. So instead what we do is we do like a log difference, which is kind of agnostic to things being really close to 0. But the cool thing, like I said, is that these are on the same scale. The fluorescence data was a little bit brighter in this case, but the patterns you see are quantitative, the same. And when you start looking at the response of one versus the response of other, the data pretty much correlates. So with all of this in mind now, what can we do with this? You guys are going to get to see examples over the next couple days of all kinds of applications of this technology. I'm just going to show you a few things that I did early on. I did this one in conjunction with Aaron. This was kind of a T-cell signaling experiment. This is something that I don't know what's happened with the T-cell signaling. I haven't done much with it lately, but it was a lot of fun to do at the beginning. And this is a figure that ended up in a lot of our lab's grant applications for CyTOF-related things. Basically, what I wanted to do here is take every T-cell signaling-related phosphorylation epitope in the lab and measure them in conjunction in a single experiment. So this is just a little time course that we did. And the point is that the data we get is very similar to fluorescence data. And even though this was done on jerkcats and it was like a T-cell line and there wasn't a lot of what we would call heterogeneity or different cell populations in the dish, turns out that even when you're dealing with something that is seemingly homogeneous or consistent, that when you drill down at a certain time point, you can subdivide based on even signaling responses, and you can actually capture different cell states happening in the same tube. And so this is just showing just using S6, which is a marker of active translation, as a reporter. You can see kind of the cells at a later time point that are already feeding back and shutting down the signaling cascade versus ones that are still turned on and active. Now, what happens when you apply all of this to something like hematopoiesis? So with this many parameters now available, so somewhere between, at this point we were at about between 30, 35 parameters, Aaron and I both thought that we could do a pretty good job of capturing everything that happens here in a single experiment and have the ability to hopefully look at some signaling responses at the same time. And so what we did is we devised a couple different panels. This was kind of the experimental setup where we chose a couple typical immune activators. We wanted to look at a drug, dasatinib, that's kind of a popular chemotherapeutic drug that is especially becoming prevalent in hematopoietic malignancies. And we applied these in conjunction with what we called our functional panel. So this functional panel consisted of 18 behavioral epitopes and a core of 13 surface markers. And these 13 surface markers we thought best approximated all of the hematopoietic lineages. But just to be certain, we added an extra panel in that contained that same core surface markers, but had 18 additional markers that we hoped would help us confirm some of the cellular identities in the experiment. And so the idea was, is with 13 dimensions of data, that we could bridge the two data sets and actually bring a lot of this information into here. And this is just a quick snapshot of what happens when you do a 30-parameter experiment on bone marrow. So you get a lot of data, and all of those cell types I just showed you on that developmental figure are there. But you kind of have to know where to look for them. So if I went in and looked for the things that I knew that I like to look for, that I knew are typically there, you can see your CD4 T cells, mature B cells, monocytes, even your progenitor cells, looking at CD34 and CD117. The problem is you have to know they're there, and we'll get back to that in a second. But with enough reading and about, well, again, I can't really take credit for this. This is more Aaron locked in his apartment for 3 weeks. He went through this data post-analysis and managed to gate out 22 pretty clean cell populations. And then we were able to look at the phosphorylation signaling responses across all those different conditions that I just showed you. And it's cool because you get this, and then you can do this kind of immunological or hematopoietic stargazing and start looking for patterns. So you can look at things like, oh, well, if you look at the hematopoietic stem cells in the progenitor cell populations, oh, well, they're kind of all signaling the same. So maybe their wiring is kind of similar. But you go a little bit more mature and you start looking at early B cells versus late B cells, you can kind of see that there's like a signaling switch that happens. So at a certain point in B cell development in the bone marrow, certain pathways become available that weren't available earlier on. So this is really cool. But like I said, this was 3 weeks in Aaron's apartment to get these cell populations. So you had to know that they were there. So you're reading, you know, we're standing on the shoulders of 25, 30 years of flow cytometry and immunology to get there. So how do you actually see in 30 dimensions? Again, I'm not gonna talk about the details of this because Aaron's actually talking about it tomorrow. But we were fortunate enough to have an algorithm that was developed in parallel with us working on this new instrumentation called SPADE that allowed us to have these dimensionality reduction visualizations. So just take it for granted that what SPADE was able to do is take the really high dimensional single cell measurements and distill them down into a two-dimensional scaffold that we could then use to browse our data. And the cool thing that I really liked about SPADE is you didn't have to know the cells were there to begin with, because every cell in your experiment that you gave to SPADE got put into one of these nodes. So each of these nodes represents a cluster of cells. And when you overlay the expression of different surface markers on these representations, you can then go and assign different cell populations. But again, I'm not going to show you how that happens because Aaron's going to show you later, and you guys are going to get to do a hands-on SPADE demonstration with the data that you're going to generate in the course. So just to give you a little insight into some of the things that happened once we had SPADE, is we were able to go and unbiasedly look at our data, and turns out a lot of canonical responses that you'd expect to see in immunology and hematopoiesis in terms of phosphorylation showed up. So you have something like B cell receptor cross-linking, you have a nice phospho-ERK response, PMAI and myosin activation, you get ERK turned on everywhere or almost everywhere. And then when we applied our drug like dasatinib, we could see that we, could, if looking at something like a cytokine versus a global response from pervanidate. So pervanidate kind of blanket turns on a lot of phosphorylation sites via inhibiting tyrosine phosphatases. So it basically turns off the negative feedback. So you upset the balance inside a cell and everything momentarily gets phosphorylated. But interestingly, something like here, you have phosphostat-5 we could actually turn off the phosphostat-5 response from pervanidate with dasatinib, but dasatinib wouldn't touch something like IL-7 phosphostat-5 in T cells, which is mediated by the JAK-STAT pathway, which isn't targeted by this drug. So you can see a lot of things that you knew were there, and you guys can go. This is all in the details are in the science paper, but there's a lot of cool things that came up that weren't expected. So just to give you an example now with the high-dimensional data and these kind of unbiased visualization techniques and how useful they can be in the case where something goes wrong. So again, we were able to do a lot of that and validate it in terms of making us feel confident to use it as a tool for research and discovery because we were, again, standing on the shoulders of 30 years of hematopoiesis and immunology. So we already knew the answers. We were just repeating it with a different platform and looking at it with a new level of resolution. But what happens when you don't know the answer, when there is no template laid out? So in the case of something like pre-B-cell ALL, normally in the bone marrow, here's your CD10 positive cells. Your CD10 positive cells are kind of your pro-pre-B cell population. This is like they've just, your hematopoietic stem cells have differentiated. They've kind of gotten past the lymphoid progenitor, and now they've committed to the B cell fate. Very, very rare. Probably more rare or as rare as hematopoietic stem cells in the bone marrow, especially the pro-B cells. With pre-B-cell ALL, what happens when you do a spade representation of leukemic bone marrow is here's your CD10 positive cells. So most of the bone marrow has been taken over. In this case, I think this particular case was 98% CD10 positive. So just a cool thing that spade can do is, well, you get this big tumor of CD10, you actually, even though we didn't have all the right markers in there, you can actually still see, of the 2% of your cells left, you can still see a lot of the normal immunological cell types. But we're not going to talk about that. We're going to talk just about the tumor here. So it gives us the ability to drill down on the tumor. So you can start looking at the expression of different markers like CD19, which is another B-cell marker, or proliferation via Ki67. So just focusing on the tumor, you start having cases where we can look at signaling much like we did in the normal situation. So you can look at translation responses to calcium ionophores like PMA and aminomycin, where everything uniformly turns on. But then you add a drug like the dasatinib that would normally maybe turn this off in the normal case, like I showed you before. What happens is half the tumor doesn't respond. Where but if you look at a different pathway like ERK, you can turn most of it off. So you can start kind of dissecting things based on expected or unexpected signaling responses. So you can, if you have a drug of interest that might target a cancer of interest, you can use these types of these approaches and high-dimensional analyses to kind of drill down and generate hypotheses to do follow-up experiments. So in this case, it was dasatinib and pre-B-cell and looking at these different pathways where, again, in a fluorescence experiment or some other experiment, you might have thought, okay, well, ERK's my readout. Well, ERK, in the case of ERK, you might have said, okay, well, the drug's pretty much working. Most of the tumor's turned off. But if your readout had been S6, you'd be like, oh, well, S6 is unaffected by this drug, and maybe that's more important because S6 is actually a marker of metabolism. I don't know what the end goal would be, but the point is when you're doing the guilt-free mass cytometry method, you have the ability to measure all of these things in one experiment. So you don't necessarily have to have a specific question at the get-go. You should have a question. You shouldn't just throw your samples at the machine, but it gives you less constraints. So now it adds a little bit more discovery into something that was traditionally a very targeted approach. So the future of mass cytometry, this week, or not this week, today and tomorrow, people are going to talk to you about multiplexing samples and drug screening and how we're able to run experiments on this machine where you can generate 20,000 data points per tube. People are going to talk to you about really, really high-dimensional T-cell analysis where by leveraging 20 plus parameters, looking at cytokines and surface markers of a T-cell, how you can actually dissect different virus-specific T-cell populations within what was thought to be a fairly homogeneous compartment. People are going to talk to you about really high-level apoptosis and cell cycle measurements, as well as kind of more of the nuts and bolts of how we can analyze this data and leverage this data to kind of look at single-cell systems in a new way. But just to give you an idea about the technology itself and where it's going, this is a picture from a figure from the very first ICP-MS paper published back in 1980. And what this is kind of a standard ICP-MS set of metal reagents. And in 1980, we were able to get, or the individual who invented this technology was able to get around 1,000 counts per second per unit of standard on his ICP-MS. Today, on the exact same instrument, or the modern equivalent of this instrument, we can now get 10 to the 9. So there's been a 1,000,000-fold improvement in sensitivity over about 30 years. And the other thing to show you is this is the current kind of spectrum of the mass cytometer. So what this is showing all the way from about 100 up to about 200, which is what the current commercial cytoph can measure. And what we put on here is kind of an equimolar solution of all the different reporter elements. And what I want to point out is there's big swaths of nothing in here. And these are all basically channels that can be filled up with reporters that exist as stable elemental isotopes. And this is actually already out of date because since Aaron and I made this kind of on a whim, we've actually filled up about, we've filled up probably another dozen channels down here. So a lot of this is going to hopefully be improved without actually improving the instrumentation. It's actually a lot of it is improving the reagents and creative ways to use new isotopes. Anyways, that's it. Nolan Lab. I got to give a lot of credit to Aaron because Aaron did pretty much all these experiments with me, and the ALL data is Kara Davis's. That's it. Thanks. So for dim markers, oh yeah, no, that's I mean I kind of breezed over that, but I think Peter talked a little bit about that. All the principles of fluorescence flow cytometry panel design, other than a lot of the dealing with compensation, apply here. So having positive and negative controls for everything and titrating your antibody on cells treated under the conditions for your assay is very important for you to know where positive and negative is. A lot of the time, negative is 0 or very close to 0, but sometimes it's not. There's a lot of parameters like I'm trying to think. Like I mean CD45 again. I kind of pick on it. But there's a lot of things like CD45 that in fluorescence you might call positive and negative, but when I look at it in mass cytometry data, the positive cells match the positive cells, but you actually get there's kind of like a mid to low population, and you get a little bit of staining on some kind of more terminally differentiated immune cell types, like like platelets, you might see a little tiny bit of CD45, and neutrophils, you might see a tiny little bit more. And so those that would normally be negative actually fall into the positive scale. And so again, having a proper negative control, something that would be CD45 negative, would be the only way to really draw that gate properly. Yeah, so we don't typically do that on an experiment by experiment basis. That usually is all done when we're titrating and characterizing the reagents. So we'll because unfortunately not a lot. There's around 25 human antibodies available now commercially, and we're starting to use those. We're going to use those in the experiments. Some of those in the experiments today, but most of our antibodies in the lab are custom conjugated. And when we run those again, it's like a positive and negative control, and you kind of get a feel for, that data we put that data up on Cytobank, or the data is available at our lab, so we kind of get a feel for where the positive cell population lies versus where our negative cells are expected to be.